This is a modified version of fundamental problem 1623. In this problem, at the instant shown, the wheel rotates with an angular velocity of 12 radians per second and an angular acceleration of 6 radians per second squared. We want to determine the angular acceleration of link BC at the instant shown. Now, the change that we're going to make in this problem is we're going to take point C and we're going to make it a point on a piston here. And this piston can only move in the horizontal direction, which means that the velocity of point C can only have an I hat component, and the acceleration of point C can only have an I hat component. It can be positive or it can be negative. The solution that they give you in the back of the book is actually for this situation, which is actually how the problem appeared in the 12th edition of the book. In the 14th edition of the book, and I don't know, it might be this way in the 13th edition also, but somewhere before the 14th edition, they changed the picture, but they did not change the solution in the back of the book. Okay, so we're going to ignore the picture here, make this a piston, kind of like the piston that we have in problem 24, but moving only in the horizontal direction. Okay, and then we're going to use equation 1618. We're looking for the angular acceleration of link BC. So we have two things which are rotating in this problem. We have this angular acceleration for the wheel. We want to find the angular acceleration of the link. So I'm in this equation, 1618, I'm going to call it angular acceleration BC so we don't get confused with the acceleration that we have over here. So if it's the angular acceleration of BC, I need to look at 2 points at this link. So I'm going to look at point B and point C. And as we saw in the previous problem, you can take that equation and you can write it with the C here, or you could take that equation and here it would be all the A's would be B's, but you could do it, here, replace the A's with the B's. You could do it either way. It would just change the sign for all the terms in the equation. So I'm going to do it this way. And before I start finding things, I just want to look at what's going to happen when I use this equation. So I know that the acceleration of point C has to be in the I hat direction. It could be positive I hat or negative I hat, but this piston cannot move in the vertical direction. So in my equation here, I'm going to take AC and call this, you could call it ACX if you want to, because it's the X component, but that's the only non-zero component that we have. So this is just in the I hat direction. The acceleration of point B, because point B is on the wheel, it has to have an acceleration pointing in towards the center of the wheel. Because this point is moving, you have to have acceleration pointing inwards. And because you have angular acceleration, you have tangential acceleration for point B also. So for B, you have an I hat component and a J hat component, or you could say a normal component and a tangential component. So we're going to have both, let's do it this way, A, B, X in the I hat direction plus A, B, Y in the J hat direction. For the angular acceleration of this link, that has to be either in the positive K hat direction or the negative K hat direction. Let's look at this cross product separately and say, let's just say it's in the K hat direction, and if ABC alpha BC comes out to be negative, then it's in the negative K hat direction, crossed with the position of C with respect to B that's going to point C from point B. So that's in the I hat direction, and they give us this length here, which is 1.2 meters. So this is 1.2 meters in the I hat direction. This I'm looking for. And that gives me K hat crossed with I hat, which is J hat. So this is 1.2 meters times alpha BC in the J hat direction. So I'm going to put that in here for the cross product. This is 1.2 meters times alpha BC in the J hat direction minus this angular velocity I wasn't given that angular velocity. I was given the angular velocity of the wheel. Now, I can find this if I need to, but I don't know it now, so we'll just leave it as the angular velocity squared times this position vector, which is the same as this position vector. That was 1.2 meters in the I-hat direction. So this is 1.2 meters in the I-hat direction. So let's look at what we would have to do in order to find my angular acceleration here. My angular acceleration appears in this term only. This is in the j-hat direction. This is in the I-hat direction. This is in the I-hat direction. This is in the I-hat direction. So if I only look at the j-hat terms, I have 0 is equal to the y component of the acceleration for point B plus 1.2 meters times the angular acceleration BC, which means this must be negative. I could actually solve for that now and say alpha BC is equal to minus the y component of the acceleration of point B divided by 1.2 meters. So really all I have to do in this problem, now granted, we modified the problem, so if we had a x component and a y component for the acceleration of point C, it would be more difficult to solve. But the way I have it now, which is the way the problem used to be, all I have to do is find the y component of the acceleration for B. Now, the acceleration for point B, we have angular acceleration going like this. So point B is going to be accelerating this way. So this is the y component of the acceleration here is going downwards, and that is tangential acceleration. So there's a normal component pointing in towards the center of the circle and a tangential component which is pointing downwards. Now, going back to my equation sheet, the tangential component for acceleration is equal to angular acceleration crossed with r. Now we're talking about the wheel here, so it's angular acceleration of the wheel crossed with r, which is going to this point from the center of the wheel. So the tangential component, or the y component, so this is a, b, y, which is the tangential component, is equal to the angular acceleration of 6 radians per second crossed with r. R is the radius here, which is 0.3 meters. That's pointing this way. And the angular acceleration, since you have angular acceleration like this, the vector's pointing downward. So it's this crossed with this. So that's actually pointed into the page, crossed with a vector which goes from A to B. So that is going from A to B. That's like this. So I have to keep my fingers pointing in towards the center, then turn them this way. So that's going in the negative j-hat direction like we showed here. So that would be negative times the 0.3 meters. So that gives me minus 1.8 meters per second for the y component. So actually this angular acceleration is going to be turning out positive because I have a negative sign here, but this is in the negative direction also. So this is minus negative 1.8 meters per second divided by 1.2 meters. 1.8 divided by 1.2 gives us 1.5 radians per second squared. What did we say about the angular acceleration here? We said it was in the k-hat direction, so because it turned out positive, it really is in the k-hat direction, so that vector is 1.5 radians per second squared, in the k hat direction, which is what they asked us to find. And this is the answer in the back of the book because we changed the problem around to agree with the answer in the back of the book. So that was a shortcut to find this. Now, maybe we also want to look at what we would get if we looked at the I hat components also. So at this point we have found what they asked us to, but let's see what else we could find if we looked at the I hat components. Okay, so going back to my equation here, now let's just write down what we have for the I hat component. So for I hat, I have AC, and this is actually the X component. Let's call it that, ACX. That's the only component, the only non-zero component that we have, is equal to the X component of my acceleration here. This doesn't have an X component, and this is minus omega BC squared times 1.2 meters. Okay, so we kind of jumped around here. This would be what I can find using my equation, using this equation here. The angular velocity and the X component of B I can find by looking at what they give me in the problem. So we did find the Y component by looking at the tangential acceleration. Now, if we had started off this problem just by looking for the acceleration of B, I would have done it this way. This is a point on the outside of the wheel here. So go back to equation 1614, and rather than just looking at the tangential component, if we look at the whole equation, we would have, let me pull this back over, angular acceleration, this is for the wheel, crossed with the position minus angular velocity squared times your position vector. So that is equation 1614. I don't really know what to call these here, but they're what we have here for the wheel, not what we have for link BC. So I already did this. So this is what I have here. The alpha crossed with the R, that gave me something going in the negative j hat direction. So this is going to give me the normal component, which is going in towards the center of the wheel in the negative I hat direction. So from what we had before, let's just say this is negative 1.8 meters per second j hat. So we're kind of combining the normal and tangential with the I hat and the j hat here. So normal's in towards the center of the circle. This is minus omega squared. This is this omega here. That's 12. So that's minus 12 radians per second squared times r, which is going from the center out towards this point. So that's 0.3 meters in the I hat direction. But this negative sign here makes the acceleration, this component of the acceleration, point in the negative I hat direction. So this is 0.3 meters I hat. So let's put the I hat component first. So 12 times 0.3 gives me 3.6. So this is minus 12 squared. So that's minus 43.2. And this is meters per second squared in the I hat direction. Why is this meters per second? What was this? This was -6, that was radians per second squared. So this was supposed to be 1.6 radians per second squared, which means this was, but this turned out in radians per second squared anyways. Okay, so 43.2 meters per second squared minus this is 1.8 meters per second squared j hat, or we can write that as minus 43.2 I hat minus 1.8 j hat meters per second squared. Okay, so now we found the acceleration of point B, and we just wanted to look at the I hat component. So I have A, C, X, and we remember we're just doing this for fun because we already answered the question there. So the X component of the acceleration of B is minus 43.2. So this is minus 43.2. This is meters per second squared. Minus omega BC squared times 1.2 meters. Okay, so now we can use what we learned in the last section about the instantaneous center of zero velocity. So in the previous section, for finding the instantaneous center of zero velocity, well, if you look at point C here, because point B is here, this is as far out as point C is going to go. So this is the turning point for point C. So the piston C was moving out this way, and then it's going to start to move back this way. So the velocity of point C at this point right here is 0. So at this instant, the velocity of point C is equal to 0 because this is a turning point. And because it's equal to 0, this is the instantaneous center of zero velocity. If this point is the instantaneous center of zero velocity, then I can say the velocity of point C is equal to the angular velocity of link BC times the, no, I don't want to do that. I want to say the velocity of point B is equal to the angular velocity of BC times the distance to point B from the instantaneous center of zero velocity, which is point C. The velocity of point B that's pointed downwards, did I find the velocity of B? I didn't find the velocity of B. I don't think I found the velocity of B, but I could find it because they gave me the 12 radians per second here. So if this is a point on the outside of the wheel, that is equal to the angular velocity times the radius. So that's 12 times 0.3. Because this is the instantaneous center of zero velocity for link BC, the velocity of point B is also equal to the angular velocity of BC times the distance from C to B, which they showed us in the book was 1.2 meters. I used it there, the 1.2 meters. So this is the angular velocity of BC times 1.2 meters. This must be equal to what I have here. So 12 times 0.3 is equal to omega BC times 1.2. Therefore, the angular velocity that I have here is 3. Okay, and I can take that, and I was using this equation here, so this is equal to minus 3, this is radians per second squared, times 1.2 meters. And now I can take this and find the x component of the acceleration for point C, which they didn't ask me to do, but we're doing it anyways. And that gives me negative 54 meters per second squared. Remember that we said the acceleration of C is just going in the x direction. So this is, well, let's circle it. They didn't ask me to find it, but I found it anyways. Okay, so that's negative 4 meters per second squared. So the velocity at this point is 0, but the acceleration is pointing in the negative I hat direction. So before we got to this point, the velocity was pointed this way and the acceleration was pointed this way, so the piston was slowing down. Then after this point here, the velocity is going to be pointed velocity is going to be pointed this way, and the acceleration is pointed this way. So after this point here, it will start speeding up. Okay, so that concludes our modified version of Fundamental Problem 23.